So this lecture continues talking about double integrals with rectangular coordinates, and we're talking about switching the order of integration. And this is something you saw in Math 126, but it wasn't explained to you in this much detail in Math 126. So in Math 126, all we told you is this top statement. We can switch the order of integration if the functions are nice. You didn't know what nice meant, so here we're telling you this, and probably in 126 we also didn't call it Fubini's theorem. So now we're giving it a name. The thing that says we can switch the order of integration is called Fubini's theorem. Fun fact, there's a Fubini, I work on Fubini words in my research, which have nothing to do with this. But Fubini did a lot of math, just like lots of mathematicians did a lot of math. You've probably seen like Euler's name on everything, for example. Okay, so what does nice mean? Nice means one of these two things. So either the function is continuous, which most of the functions you've seen have been up to this point, continuous in the whole region and defined on the whole region. Or it's bounded on the region. Bounded just means it doesn't go to positive or negative infinity, basically. So technically, it means you can find a value that's larger than or equal to every value it takes in the region and smaller than or equal to. And the times when it tends not to be bounded is when it's not defined on the boundary. It doesn't have to be defined on the boundary, but sometimes when it's not defined, it could go to positive or negative infinity there. And we'll actually see an example of that. And the other way that we make sure it's not too bad is that it has finitely many discontinuity curves. What does that mean? Well, here let me draw a staircase. So this is like a modern staircase. There's no vertical part holding it up. Maybe there's poles. The poles aren't part of the function. So there's the poles. And now if your surface is the top surface of this staircase, so that's your f of xy, z equals f of xy, then these are the discontinuity curves. It's discontinuous on that whole line. These are actually lines of discontinuity, but they could be curved. We could go, we could make an even more modern staircase. So what happens, well, let's say your region is just these three stairs. Then in the xy plane, what that looks like is we've got these discontinuity curves. So there just has to be finitely many of those, not infinitely many. So you can imagine that second condition is pretty difficult to break, at least with functions that we can write down, like f of x comma y equals something. Certainly functions exist. You can make lots of random functions. In fact, most functions are what we call wild functions. Can't write them down explicitly. However, in this class we'll continue to deal with functions we can write down explicitly. So wild functions are not that interesting to study because they just don't have that many good properties. So let's look at this function though. This function actually does break this the conditions of Fubini's theorem. So let's see, we're looking at it on this region. Always got to look at a function on a region. You can look at it on the whole xy plane, but then you would be doing improper integrals, which is fine. Okay, so we're on the unit square region, which we know and love. And what's wrong with this? It actually looks like it's going to be continuous. So here's the point where it's an issue. It's an issue at 0, 0. It's not continuous there because it's not defined there, right? It's actually an indeterminate form, 0 over 0. So we've got to figure out how bad the indeterminate form is, and the answer is it's pretty bad. Why is it pretty bad? Well, okay, so we don't have a higher dimensional analog of L'Hopital's rule yet, so we can't use that to explain why it's pretty bad. So we'll just do a little bit of a hand-wavy explanation. The top is approximately 0 squared, a small number squared, so that's quite small. But the bottom is 0 squared squared, small number to the fourth, so it's even smaller. So the top is not going to shrink as fast as the bottom. Unless x and y are really close together, which we're not guaranteeing. So what that means is that the limit as x comma y goes to 0, 0 of f of xy is infinity, basically. It could actually be, depending on whether x or y is bigger, it could be in absolute value, it could be positive or negative infinity, so that's even worse. So it's pretty bad. This function is bad enough at 0, 0 that it's going to wreck the whole integral on that unit square. So what we're going to do is we're going to integrate it two different ways, and we'll see that we get two different answers. Okay, next. The functions that don't satisfy the conditions of Fubini's theorem are a little bit weird. So the integration is going to be a little bit weird. So I apologize for that. Basically, the technique of integration is inspection and be really smart. So this is not a technique that you would be expected to know on a quiz or test. I wouldn't be able to come up with this on a quiz or test. You have to be really, really smart. So I will show you what it is. You should recognize that it's correct. That's what you're expected to do. Okay, so first we're going to do an algebra trick. There's the algebra trick. So why are we doing this? Because we're really smart. Oh, we may not be, but we're pretending we are. So all you have to do right now is recognize that that's the same as that. Agree that that simplifies to that, right? Okay, now let's see. I'm going to be a little bit smarter even. So I'm going to put a 1 times that there, and then minus, I'm going to put a y times 2y. That's the same as what I had before, right? That was 2y squared. Okay. Okay, so why are we doing this? Well, now this is a quotient rule. It almost looked like a quotient rule at the beginning. We had a bottom squared. So maybe if you were smart enough to figure this out, which I am not, that's how you would do it. You would see that this bottom squared, and you would be a little bit tenacious about the top and figure out that it could look like this. And so what I claim is that that thing is the derivative of this thing, y over x squared plus y squared. And if that's right, then I'm allowed to integrate it, and I'm allowed to plug in bounds and keep going. Let's just make sure it's right. So let's see. We're taking derivative with respect to y because we have dy on the inside. So what is this? This is derivative of y, which is 1, times the bottom, that looks right so far, minus, that's part of the quotient rule formula, y, that's the top, times the derivative of the bottom, that's holding x constant, over the bottom squared. Okay, so you don't have to be able to do this to figure out that it's this, but you do have to recognize that the derivative is that. Okay, so as long as that's all right, then we can plug in bounds and carry on. So integral from 0 to 1, we're going to put in 1 for y, 1 over x squared plus 1, minus, if we put in 0 for y, we get 0. Make sure you check that. It's not always the case that when you put in 0, you get 0, but here it is. Okay, and here's an integral that maybe you have memorized that I don't. That's arctan from 0 to 1. Fun way to do arctan is if you just draw a line with that slope. So line with slope 1 looks like that, and that angle is 45 degrees or pi over 4. So arctan of 1 is pi over 4. You just pick the angle between negative pi over 2 and pi over 2 that line makes with the positive x-axis. And then a line with slope 0 makes an angle of 0. So pi over 4 minus 0. So, okay, we integrated this. Maybe we couldn't have done this without help. This is the example in Samantha Fairchild's notes. And it took me a while to figure out how to get this integral. But the way to get it is to be smart. All right, so anyways, we somehow did this. We did it with dy on the inside, and we got an answer of positive pi over 4. Let's do it again with dx on the inside, so you can see that Fubini's theorem doesn't work. X squared minus y squared over x squared plus y squared squared. This one is even a little bit more contrived. Same technique, harder to think of. The other one, you know, maybe you could convince me that on the smartest day of my life, I might be able to figure that out. This one, no way. Never. I am not smart enough for this. Okay, so same thing. You just have to agree that this is right. I'm doing an algebra trick to unsimplify this for some reason. Agree that if I simplified it, I could get back to the top one. Haven't changed anything. And now I'm going to rewrite the plus 2x as minus negative x times 2x. See, negative signs make things a lot harder. Here now there's no way I could have guessed to write it like this and to use the quotient rule. Okay, so now I'm claiming that negative x over x squared plus y squared has derivative that. And if that's true, then I can plug in values. Okay, let's make sure we believe that. What are we doing? We're taking derivative with respect to x now. So derivative of the top is negative 1 times the bottom. Minus, that's part of the quotient rule. The top, negative x. Derivative of the bottom is 2x, if I hold y constant, over the bottom squared. All right, that's apparently right. So as long as we believe that the derivative of this function that I made up is this uglier function that is apparently the unsimplified version of the thing we started out with, we're good. We can do this integral. Again, would not expect you to come up with this. All right, integral from 0 to 1. We're going to plug in 1, which is negative 1 over 1 plus y squared. Plug in 0, we get 0. That's now integrating with respect to y. So, oh, this is weird. Now we get negative arctan of y going from 0 to 1. So we get the opposite result from before. We get negative pi over 4. So, indeed, if I hadn't checked whether this function satisfied the conditions of Fubini's theorem, and I just picked one of these ways to integrate it, I said it doesn't matter because of Fubini's theorem, I'd have been wrong. And if I told you guys to do it and didn't tell you guys to check, half of you would have gotten pi over 4, half of you would have gotten negative pi over 4, and we would have wondered who's wrong. Okay, so before I end this video, let's do one that's right, and let's do one where we need to do it. So we're going to move out of rectangular regions. E to the y squared dy dx. Okay, and you saw how to do this in Math 126, so this is just a quick review. E to the y squared is really hard to integrate. Don't know how to integrate that. Need a thing called complex analysis, which you don't know yet. So let's see. Always draw a picture of the region, especially if it's not a rectangle. So x is going from 0 to 1. So if I put 1 there, x is going up to here. Pretend that goes through 1. And then y is going, so these are actually curves. This is the curve y equals 1. This is the curve y equals x. So I've got to draw y equals x and y equals 1. And then what's the region? As x goes from 0 to 1, y goes from x up to 1. Make sure you shade in the right part. So right now we're integrating with vertical lines. And now, to switch the order of integration, we want to go to horizontal lines. So we want to go to these things. So what does that say? That says, function's not going to change, y squared. That says as y goes from 0 to 1, 0 to 1, dy is on the outside, then x, the horizontal line, is going to go from 0 to this curve, y equals x. So x is going to go from 0 to y. Impossible to guess how these things change. Like this, those numbers, you can't guess that it's going to change this unless you draw the picture. So you must draw a picture. There's going to be more complicated things going on in this class. You must draw a picture for those as well. All right. Why is this better? Well, at least we can do the inside integral because this whole thing is a constant. So that's great. So we can just do e to the y squared and x. X goes from 0 to y. And then we plug in our bounds. And then magically, so plug in y, we get y, minus plug in 0, we get 0. It won't always happen, but it certainly has happened so far. And then magically, we can now do a u substitution. Because thankfully, this y showed up. Du is 2y dy. So y dy is 1/2 du. I have a y dy, I can replace it with 1/2 du. So integral from, so you have a choice. You can either switch the bounds or you can leave them. I'm going to leave them. I think that's less work. It's up to you. This is e to the y now, e to the u now. Y squared is u, and then I have a 1/2 du. Okay, so I'm going to integrate. I get 1/2 e to the u. Integral of e is just e to the u is just e to the u. And then I've got to switch back. U was y squared. So 1/2 e to the y squared as y goes from 0 to 1, which is 1/2 e to the 1 minus 1/2 e to the 0. E to the 0 is 1. Aha! So plug in 0 doesn't always give you 0. All right, so there's the answer to that one. Could not have found that if I had started with my original thing. I just would have been stuck forever. So Fubini's theorem certainly helps us.